Good day everyone. This is Mikey Dayan Talarok and I am here to discuss on chapters 11, 12, and 13 from Vector Mechanics for Engineers, Statics, and Dynamics. Chapter 11, Kinetics of Particles. Before we begin discussing the topics, let's first review dynamics, which is a primary subject of this lesson. The first significant contribution to dynamics was made by Galileo. Galileo's experiments on uniformly accelerated bodies led Newton to formulate his fundamental laws of motion. Dynamics includes kinematics, which is a study of the geometry of motion. Kinematics is used to relate displacement, velocity, acceleration, and time, without reference to the cause of the motion. Kinetics, which is the study of the relation existing between the forces acting on a body, the mass of the body, and the motion of the body. Kinetics is used to predict the motion caused by given forces or to determine the forces required to produce a given motion. Rectilinear motion of particles. A particle moving along a straight line is said to be in rectilinear motion. In the video flashed on your screens, a motorcycle is shown moving straight forward on a street. This is a good illustration of which an object is in rectilinear motion.
In rectilinear motion, position, velocity, acceleration of particle moves along a straight line. Or simply we say that when body move along a straight line is called rectilinear motion. For example, march first of army. 2. Elevator. 3. Car or train moves along a straight line.
The average velocity of the particle over the time interval is defined as the quotient of displacement and the time interval. The instantaneous velocity of the particle at the instant is obtained from the average velocity by choosing shorter and shorter time intervals and displacements. The average acceleration of the particle over time interval is defined as the quotient of delta v and delta t. The instantaneous acceleration of a particle at the instant is obtained from the average acceleration by choosing smaller and smaller values for delta t and delta v. The limit of the quotient, which is defined by the derivative of v with respect to t, measures the rate of change of the velocity. We can write it by a is equal to dv over dt. The acceleration a is represented by an algebraic number which can be positive or negative. A positive value of a indicates that the velocity increases. This may mean that the particle is moving faster in the positive direction or that it is moving more slowly in the negative direction. In both cases, delta v is positive. A negative value of a indicates that the velocity decreases. Either the particle is moving more slowly in the positive direction or it is moving faster in the negative direction. Example: consider a particle moving in a straight line and assume that its position is defined by the equation x is equal to 6t squared minus t cubed, where t is expressed in seconds and x in meters. The velocity at any time is obtained by differentiating x with respect to t. So, from the given equation, x is equal to 6t squared minus t cubed, it becomes v is equal to dx minus dt is equal to 12t minus 3t squared. Next is the acceleration. The acceleration is obtained by differentiating the equation that we got for the velocity with respect to t. So, from the equation v is equal to 12t minus 3t squared, it becomes a is equal to dv over dt equals 12 minus 6t. There are three common classes of motion. First is that the acceleration is a given function of t. Second, the acceleration is a given function of x. And third, the acceleration is a given function of v. Uniform rectilinear motion is a type of straight line motion which is frequently encountered in practical applications. In this motion, the acceleration of a particle is zero for every value of t. The velocity is therefore constant. So the equation dx over dt is equal to v becomes constant. The position coordinate x is obtained by integrating this equation, denoting by x sub 0 the initial value of x, and it resulted to an equation of x is equal to x sub 0 plus v times t. This equation can be used only if the velocity of the particle is known to be constant. Uniformly accelerated rectilinear motion is another common type of motion. In this motion, the acceleration of a particle is constant, in which dv over dt is equal to a becomes constant. The velocity of the particle is obtained by integrating this equation. So the equation becomes v is equal to v sub 0 plus a times t, where v sub 0 is the initial velocity. Substituting for v in the equation, v is equal to dx over dt, so we write dx over dt is equal to v sub 0 plus a times t, denoting by x sub 0 the initial value of x, and integrating, then we got the value of x, which is equal to x sub 0 plus v sub 0 times t plus 1/2 times a times t squared. Relative motion of two particles. Consider two particles, A and B, moving along the same straight line. If the position coordinates x sub A and x sub B are measured from the same origin, the difference x sub B minus x sub A defines the relative position coordinate of B with respect to A and is denoted by x sub B over A. Then we write the equation x sub B over A is equal to x sub B minus x sub A, or written as x sub B is equal to x sub A plus x sub B over A. Based on the figure below, we can see that the distance from 0 to A is denoted by x sub A. This means that it measures the distance between these 2 points. And from point A to B, it denotes x sub B over A, which measures the distance between A and B. And from 0 to B, it is denoted by x sub B, which it measures the distance from 0 to B, which includes the point A in the middle. The rate of change of x sub B over A is known as the relative velocity of B with respect to A, and is denoted by v sub B over A. And the equation can be written as v sub B over A, which is equal to v sub B minus v sub A, or v sub B equals v sub A plus v sub B over A. A positive sign for v sub B over A means that B is observed from A to move in the positive direction. A negative sign means that it is observed to move in the negative direction. The rate change of v sub B over A is known as the relative acceleration of B with respect to A, and is denoted by small letter a sub B over A. Then, we obtain the equation of a sub B over A equals a sub B minus a sub A, or can be written as a sub B equals a sub A plus a sub B over A. Dependent motions. Sometimes the position of a particle will depend upon the position of another particle or of several other particles. The motions are then said to be dependent. For example, the position of block B in the figure depends upon the position of block A. Since the rope A, C, D, E, F, G is of constant length, and since the lengths of the portions of rope C, D, and EF wrapped around the pulleys remain constant, it follows that the sum of the lengths of the segments AC, DE, and FG is constant. Observing that the length of the segment AC differs from x sub A only by the constant, and that similarly the lengths of the segments DE and FG differ from x sub B only by a constant, then can be written as x sub A plus 2x sub B equals constant. Since only one of the two coordinates, x sub A and x sub B, can be chosen arbitrarily, we say that the system shown in the figure has a 1 degree of freedom. From the relation between the position coordinates x sub A and x sub B, it follows that if x sub A is given an increment change of x sub A, that is, if block A is lowered by an amount delta x sub A by the coordinate x sub B will receive an increment delta x sub B equals negative 1/2 delta x sub A. In other words, block B will rise by half the same amount. This can easily be checked directly from the figure. In the case of the three blocks, we can again observe that the length of the rope which passes over the pulleys is constant, and thus the following relations must be satisfied by the position coordinates of the three blocks. Then, the equation becomes 2 x sub A plus 2 x sub B plus x sub C equals constant. Example: a ball is thrown vertically upward from the 12-meter level in an elevator shaft with an initial velocity of 18 meters per second. At the same instant, an open platform elevator passes the 5-meter level, moving upward with a constant velocity of 2 meters per second. Determine A, when and where the ball will hit the elevator. B, the relative velocity of a ball with respect to the elevator when the ball hits the elevator. Since the ball has a constant acceleration, its motion is uniformly accelerated. Placing the origin of the y-axis at ground level and choosing its positive direction upward, we find that the initial position is 12 meters, the initial velocity is 18 meters per second, and the acceleration is negative 9.81 meter per second squared. Substituting these values in the equations for uniformly accelerated motion, we got for equation 1, v sub p is equal to v sub 0 plus a times t becomes 18 minus 9.81 times t. For equation 2, y sub p minus y sub 0 plus v sub 0 times t plus 1/2 times a times t squared becomes 12 plus 18 times t minus 4.905 times t squared. Since the elevator has a constant velocity, its motion is uniform. Again, placing the origin at the ground level and choosing the positive direction upward. We note that y sub 0 is equal to 5 meters. And for our equation 3, we got v sub e is equal to positive 2 meter per second. Positive y sub e is equal to y sub 0 plus v sub e times t, which is equal to 5 plus 2 times t. We first note that the same time t and the same origin were used in writing the equations of motion of both the ball and the elevator. We see from the figure that when the ball hits the elevator, y sub e becomes equal to y sub b. Substituting for y sub e and y sub b from equation 2 and 4 into equation 5, we got 5 plus 2 times t is equal to 12 plus 18 times t minus 4.905 t squared. We got 2 t roots, which are t is equal to negative 0.39 and t is equal to 3.65. Only the root t is equal to 3.65 seconds corresponds to a time after the motion has begun. Then substitute the value of t that we got to equation 4. Then it becomes y sub e is equal to 5 plus 2 times 3.65, which our answer is 12.30 meters, elevated from the ground. The relative velocity of the ball with respect to the elevator is v sub b over e is equal to v sub b minus v sub e, which is equal to 18 minus 9.81 times t minus 2. Then becomes 16 minus 9.81 times t. When the ball hits the elevator at time t is equal to 3.65, our v sub b over e is equal to negative 19.81 meter per second. The negative sign means that the ball is observed from the elevator to be moving in a negative sense, which means downward. Curvilinear motion of particles. When a particle moves along a curve other than a straight line, we say that the particle is in curvilinear motion.
Motion, position, velocity, acceleration of particle moves a curved path. Or simply we can say when a body moves along a curved path, the motion which is produced is called curvilinear motion. For example, a stone being thrown into the air demonstrates curvilinear motion. And throwing paper airplanes or paper darts is an example of curvilinear motion.
Rectangular components of velocity and acceleration. When the position of a particle is defined at any instant by its rectangular coordinates x, y, and z, it is convenient to resolve the velocity and acceleration of a particle into rectangular components. Resolving the position vector of the particle into rectangular components, we have the equation r is equal to x times I plus y times j plus z times k, where the coordinates x, y, z are functions of t. For velocity, we have the equation v times dr over dt equals x times I plus y times j plus k z times k. For acceleration, we have a is equal to dv over dt is equal to x times I plus y times j plus z times k. Example: a projectile is fired from the edge of a 150-meter cliff with an initial velocity of 180 meters per second at an angle of 30 degrees with the horizontal. Neglecting air resistance, find A, the horizontal distance from the gun to the point where the projectile strikes the ground, B, the greatest elevation above the ground reached by the projectile. The vertical and the horizontal motion will be considered separately. For the vertical motion using uniformly accelerated motion, choosing the positive sense of the y-axis upward and placing the origin at the gun, then we got v sub y initial is equal to 180 meter per second times sine 30 degrees, which is equal to positive 90 meter per second. And our acceleration is equal to negative 9.81 meter per second squared. Then, substituting into the equations of uniformly accelerated motion, we have for equation 1, v sub y is equal to v sub y initial plus a times t, which is equal to 90 minus 9.81 times t. For equation 2, y is equal to v sub y initial times t plus 1/2 times a times t squared, which is equal to 90 times t minus 4.90 times t squared. Then for equation 3, v squared y is equal to v sub y squared initial plus 2 times a times y, which is equal to 8,100 minus 19.62 y. For the horizontal motion using uniform motion, choosing the positive sense of the x-axis to the right, then we have v sub x initial is equal to 180 meter per second times cos 30 degrees, which is equal to positive 155.9 meter per second. Substituting into the equation of uniform motion, we obtain x is equal to v sub x initial times t, which will resort to x is equal to 155.9 times t, which is also our equation 4. When the projectile strikes the ground, we have y is equal to negative 150 meters. Carrying this value into equation 2 for the vertical motion, we write negative 150 is equal to 90 times t minus 4.90 times t squared, which is equal to t squared minus 18.37t minus 30.6 equals 0, which the root is t is equal to 19.91. Then, also substituting the value of t into equation 4 for the horizontal motion, we obtain the value of x. X is equal to 155.9 times 19.91, and our x is 3,100 meters. When the projectile reaches its greatest elevation, we have v sub y is equal to 0. Carrying this value into equation 3 for the vertical motion, we write 0 is equal to 8,100 minus 19.62y, and we got our value of y, which is equal to 413 meters. In getting the greatest elevation above ground, we will add 150 meters and 413 meters, and we have a final answer of 563 meters. Chapter 12, Kinetics of Particles, Newton's second law. Newton's second law can be stated as, if the resultant force acting on a particle is not zero, the particle will not have an acceleration proportional to the magnitude of the resultant and in the direction of this resultant force. Newton's second law of motion is best understood by imagining the following experiment. A particle is subjected to a force F1 of constant direction and constant magnitude F1. Under the action of the force, the particle is observed to move in a straight line and in the direction of the force. By determining the position of the particle at various instants, we find that its acceleration has a constant magnitude a1. If the experiment is repeated with forces F2, F3, and so on, of different magnitude or direction, we find each time that the particle moves in the direction of the force acting on it and that the magnitudes a1, a2, a3, and follows of the accelerations are proportional to the magnitudes f1, f2, f3 of the corresponding forces. The constant value obtained for the ratio of the magnitudes of the forces and accelerations is a characteristic of the particle under consideration. It is called the mass of the particle and it's denoted by m. When the particle of mass is acted upon by the force and the acceleration of the particle must therefore satisfy the relation F is equal to m times a. This relation provides a complete formulation of Newton's second law. It expresses not only that the magnitude of F and A are proportional, but also that the vectors F and A have the same direction. We should note that F is equal to m times A still holds when F is not constant but varies with time in magnitude or direction. The magnitudes of F and A remain proportional, and the two vectors have the same direction at any given instant. However, they will not, in general, be tangent to the path of the particle. When the particle is subjected simultaneously to several forces, it should be replaced by summation of F is equal to m times A, where summation of F represents the sum or resultant of all the forces acting on the particle. Example, a 20-pound block rests on a horizontal plane. Find the magnitude of the force P required to give the block an acceleration of 10 feet per second squared to the right. The coefficient of kinetic friction between the block and the plane is m sub k is equal to 0.25. First, we will solve for the mass of the block, which is m is equal to w over g is equal to 6.21 pound times s squared per feet. We note that F is equal to m sub k times n is equal to 0.25 n and that A is equal to 10 feet per second squared, expressing that the forces acting on the block are equivalent to the vector MA. Then we got these following equations 1 and 2. Solving for n and substituting the result into equation 1, we obtain n is equal to p sine 30 degrees plus 200 pound, which leads to p cosine 30 degrees minus 0.25 times p sine 30 degrees plus 200 pound, which is equal to 62.1 pound. And we got a final answer of P is equal to 151 pounds. Angular momentum of a particle. Rate of change of angular momentum. Consider a particle P of mass m moving with respect to a Newtonian frame of reference O sub xyz. The linear momentum of the particle at a given instant is defined as the vector mv obtained by multiplying the velocity of a particle by its mass. The moment about O of the vector mv is called the moment of momentum or the angular momentum of a particular about O at that instant and is denoted by h sub O. Recalling the definition of the moment of a vector and denoting by r the position vector of P is h sub O is equal to r times m times v. Motion under a central force. Conservation of angular momentum. when the only force acting on a particle P is a force F directed toward or away from a fixed point O, the particle is said to be moving under a central force, and the point O is referred to as a central of force. Since the line of action of F passes through O, we must have summation of m sub O is equal to 0 at any given instant. Newton's law of gravitation. As you saw in the preceding section, the gravitational force exerted by the Sun on a planet or by the Earth on an orbiting satellite is an important example of a central force. In this section, you will learn how to determine the magnitude of a gravitational force. In his law of universal gravitation, Newton states that the two particles of masses m and m at a distance r from each other attract each other with equal and opposite forces, F and negative F, directed along the line joining the particles. The common magnitude F of the two forces is F is equal to G times big letter M times M over R squared. Example: a block P of mass m can slide freely on a frictionless arm OA which rotates in a horizontal plane at a constant rate mu. Knowing that B is released at a distance r sub 0 from O expressed as a function of r, a, the component v sub r of the velocity of P along OA, b, the magnitude of the horizontal force F exerted on by B by the arm OA. Since all other forces are perpendicular to the plane of the figure, the only force shown acting on B is a force perpendicular to OA. For equations of motion using radial and transverse components, we got this equation 1 and 2. Letter A, component v sub r of velocity, since Vr is equal to r, then we have this equation, which leads to our final Vr is equal to u sub O times r squared minus r squared initial times to the power of 1/2. B, horizontal force F, then we got a final answer of F is equal to 2 times mu squared initial times r squared minus r squared initial to the power of 1/2. Application to space mechanics. After the last stages of their launching rockets have burned out, Earth satellites and other space vehicles are subjected to only the gravitational pull of the Earth. Their motion can therefore be determined, which govern the motion of a particle under a central force after F has been replaced by the expression obtained for the force of gravitational attraction. Force is equal to G times big letter M small letter m over r squared is equal to G m u squared, where m is a mass of Earth, small letter m mass of space vehicle, r is a distance from center of Earth to vehicle, and u is equal to 1 over r. And we obtain the differential equation. Periodic time. An important characteristic of the motion of an Earth satellite is the time required by the satellite to describe its orbit. This time, known as the periodic time of the satellite, is denoted by t. We first observe in a view of the definition of a real velocity that t can be obtained by dividing the area inside the orbit by the real velocity. Nothing that the area of an ellipse is equal to density times a times b, where a and b denote the semi-major and semi-minor axes, respectively, and that the real velocity is equal to h over 2. Then, we can write t is equal to 2 times density times a times b all over h. While h can be readily determined from R sub O and V sub O in the case of a satellite launched in the direction parallel to the surface of the Earth, the semi-axes A and B are not directly related to the initial conditions. Chapter 13. Kinetics of Particles, Energy and Momentum Methods. In the Chapter 12, most problems dealing with the motion of particles were solved through the use of the fundamental equation of motion, which is the equation F is equal to m times a. Given a particle acted upon by a force, we could solve this equation for the acceleration. Then, by applying the principles of kinetics, we could determine from A the velocity and position of the particle at any time. Using the equation F is equal to m times a, together with the principles of kinematics allows us to obtain two additional methods of analysis, the method of work and energy and the method of impulse and momentum. The advantage of these methods lies in the fact that they make the determination of the acceleration unnecessary. Indeed, the method of work and energy directly relates force, mass, velocity, and displacement, while the method of impulse and momentum relates force, mass, velocity, and time. Work of a force. We will first define the terms displacement and work as they are used in mechanics. Consider a particle which moves from point A to a neighboring point A kappa. If R denotes the position vector corresponding to point A, the small vector joining A and A kappa can be denoted by the differential dr. The vector dr is called the displacement of the particle. Now, let us assume that a force F is acting on the particle. The work of force corresponding to the displacement dr is defined as the quantity du is equal to F times dr, obtained by forming the scalar product of the force and the displacement dr, denoting by F and ds respectively the magnitudes of the force and the displacement, and by a angle formed by F and dr. Work of a constant force in rectilinear motion. When a particle moving in a straight line is acted upon a force F of constant magnitude and of constant direction, the formula yields to U sub 1y2 is equal to F times cos angle times change of x, where A is the angle of the force forms with direction of motion and delta x is the displacement from A1 to A2. Work of the force of gravity. The work of the weight of a body of a force of gravity exerted on that body is obtained by substituting the components of W. With the y-axis chosen upward, we have F sub x is equal to 0, F sub y is equal to negative W, and F sub z is equal to 0, where the change of y is a vertical displacement from A1 to A2. The work of the weight is thus equal to the product of W and the vertical displacement of the center of gravity of the body. The work is positive when delta y is less than 0, that is, when the body moves down. Work of the force exerted by a spring. Consider a body A attached to a fixed point B by a spring. It is assumed that the spring is under form when the body is at A sub 0. Experimental evidence shows that the magnitude of the force F exerted by the spring on the body A is proportional to the deflection x of the spring measured from the position A sub 0. So we can have F is equal to k times x, where k is a spring constant. Work of a gravitational force. Two particles of mass and m at a distance r from each other attract to each other with equal and opposite forces F and negative F directed along the line joining the particles and of magnitude. So this is the formula of F. Power is defined as the time rate at which work is done. In the selection of a motor or engine, power is much more important criteria than is the actual amount of work to be performed. Either a small motor or a large power plant can be used to do a given amount of work, but the small motor may require a man to do the work done by the power plant in matter of minutes. If delta U is the work done during the time interval, delta T, then the average power during that time interval is average power is equal to delta U over delta T. Letting delta T approach 0, then we obtain at the limit power is equal to du over dt. The mechanical efficiency of a machine was defined as the ratio of the output work to the input work, where H is equal to output work over input work. This definition is based on the assumption that work is done at a constant rate. The ratio of the output to the input work is therefore equal to the ratio of the rates at which output and input work are done. And we have H is equal to power output over power input. Because of energy losses due to friction, the output work is always smaller than the input work. And consequently, the power output is always smaller than the power input. The mechanical efficiency of a machine is therefore always less than 1. Example, an automobile weighing 4,000 pounds is driven down a 5-degree incline at the speed of 60 when the brakes are applied, causing a constant total braking force of 1,500 pounds. Determine the distance traveled by the automobile as it comes to a stop. To determine the distance traveled by the automobile as it comes to a stop, first we need to find its positions by using the kinetic energy. For position 1, we have V sub 1, which is equal to 60 miles per hour. We will just convert it to feet per second. So our V1 becomes 88 feet per second. And we got T1, T sub 1, using the formula 1/2 times mv squared sub 1. Then we got a value of T1, which is equal to 481,000 feet per pound. For position 2, basing on the problem, we have V sub 2 is equal to 0 and T sub 2 is equal to 0. Next is finding the work using the equation of U sub 1 Y2. And we got its value of negative 1151x. So in determining the value of x, which is our distance, we need to use the principle of work and energy, which is the equation T sub 1 plus U sub 1 Y2 is equal to T sub 2. And we got a final answer of x, which is equal to 418 feet. Principle of impulse and momentum. A third basic method for the solution of problems dealing with the motion of particles will be considered now. This method is based on the principle of impulse and momentum and can be used to solve problems involving force, mass, velocity, and time. It is of particular interest in the solution of problems involving impulsive motion and problems involving impact. Consider a particle of mass acted upon by a force. Newton's second law can be expressed in the form F is equal to d over dt times m times v, where mv is the linear momentum of the particle. Impulsive motion. A force acting on a particle during a very short time interval that is large enough to produce a definite change in momentum is called an impulsive force, and the resulting motion is called the impulsive motion. For example, look at in the figure. When a baseball is struck, the contact between the bat and the ball takes place during a very short time interval. But the average value of the force exerted by the bat on the ball is very large, and the resulting impulse change t is large enough to change the sense of motion of the ball. When impulsive forces act on a particle, it becomes m times v sub 1 plus summation of f times delta t is equal to m times v squared. Any force which is not an impulsive force may be neglected, since the corresponding impulse of force times delta t is very small. Non-impulsive forces include the weight of a body, the force exerted by a spring, or any other force which is known to be small compared with an impulsive force. Unknown reactions may or may not be impulsive. Their impulses should therefore be included as long as they have not been proved negligible. The impulse of the weight of a baseball considered above, for example, may be neglected. If the motion of the bat is analyzed, the impulse of the weight of the bat can also be neglected. The impulses of the reactions of the player's hand on the bat should be included. These impulses will not be negligible if the ball is incorrectly hit. Example: an automobile weighing 4,000 pounds is driven down a 5-degree incline at a speed of 60 miles per hour when the brakes are applied, causing a constant total braking force applied by the road on the tires of 1,500 pounds. Determine the time required for the automobile to come to a stop. For the solution, in finding the value of t, we apply the principle of impulse and momentum. Since each force is constant in magnitude and direction, each corresponding impulse is equal to the product of the force and of the time interval t. Using m times v1 plus summation of imp sub 1y2 is equal to mv2. For the positive downward components, m times v1 plus w sine 5 degree times t minus ft is equal to 0. Plug in the corresponding values, and to get the value of t, we will simplify this equation. And our final answer is t is equal to 9.49 seconds. Example 2. A 4-ounce baseball is pitched with a velocity of 80 feet per second toward a batter. After the ball is hit by the bat P, it has a velocity of 120 feet per second in the direction shown. If the bat and the ball are in contact 0.015 second, determine the average impulsive force exerted on the ball during the impact. In solving the value of the average impulsive force exerted on the ball during the impact, we apply the principle of impulse and momentum to the ball. Since the weight of the ball is non-impulsive force, it can be neglected. So, we can find the force using the values of force exerted on the x and y axis. In getting those two forces, we will use this as our working equation, the equation m times v1 plus summation of imp sub 1y2 is equal to m times v2. For the x components, we will use the equation negative m times v1 plus f sub x delta t, which is equal to m times v2 cosine 40 degrees. Substitute all the values needed, simplify, solve, and we got a value of f sub x is equal to positive 89.0 pound. For the y components, the equation used is 0 plus f sub y times delta t is equal to m times v2 times sine 40 degrees. Substitute all the values needed, simplify, and we got a value of f sub y is equal to positive 39.9 pound. From its components f sub x and f sub y, we determine the magnitude and direction of the force, which is force is equal to 97.5 pound at the angle 24.2 degrees. A collision between two bodies which occurs in a very small interval of time and during which the two bodies exert relatively large forces on each other is called an impact. The common normal to the surfaces in contact during the impact is called the line of impact. If the mass centers on the two colliding bodies are located on the same line, the impact is a central impact. Otherwise, the impact is said to be eccentric. If the velocities of the two particles are directed along the line of impact, the impact is said to be a direct impact. If either or both particles move along a line other than the line of impact, the impact is said to be an oblique impact. Direct central impact. Consider two particles A and B of mass m sub A and m sub B, which are moving in the same straight line and to the right with known velocities VA and VB. If VA is larger than VB, particle A will eventually strike particle B. Under the impact, the two particles will deform, and at the end of the period of deformation, they will have the same velocity u. A period of restitution will then take place, at the end of which, depending upon the magnitude of the impact forces and upon the materials involved, the two particles either will have regained their original shape or will stay permanently deformed. Our purpose here is to determine the velocities v'(A) and v'(B) of the particles at the end of the period of restitution. Considering first the two particles as a single system, we note that there is no impulsive external force. Thus, the total momentum of the two particles is conserved, and we will write this in an equation of m sub A times v sub A plus m sub B times v sub B is equal to m sub A times v'(A) plus m sub B v'(B). Since all the velocities considered are directed along the same axis, we can replace the equation obtained by the following relation involving only scalar components. The equation becomes m sub A times v sub A plus m sub B times v sub B plus m sub A times v'(A) plus m sub B times v'(B). Example: a 20 mg railroad car moving at a speed of 0.5 meter per second to the right collides with a 35 mg car which is at rest. If after the collision, the 35 mg car is observed to move to the right at a speed of 0.3 meter per second, determine the coefficient of restitution between the two cars. In the figure, we can see that m sub A times v sub A plus m sub B times v sub B is equal to m sub A times v'(A) plus m sub B times v' sub B. which our V sub A is equal to 0.5 meter per s, our V sub B is equal to 0, our MA is equal to 20 mg, our MB is equal to 35 mg, our V prime B is equal to 0.3 meter per second, and the unknown in the problem is the V prime sub A. So in this type of problem, we will use the equation of M sub A times V sub A plus M sub B times V sub B is equal to M sub A times V prime sub A plus M sub B times V prime sub B. Substitute all the values needed, and we got the unknown values of V prime A is equal to 0.025 meter per s. And the required in the problem, which is a coefficient of restitution between the two cars, we can find its value by using this equation. E is equal to, and substitute all the values needed, we got the value of our coefficient of restitution, which is equal to 0.65. That's all for today's lecture video. Thank you for watching, and I hope this lecture video will be helpful for your vector mechanics for engineers, statics, and dynamics course.